So we are talking about set of distributions where the statistics tend to follow. Those four distributions are normal distribution, t-distribution, and then chi-square distribution as well as f distribution. The t-distribution is called as student's t-distribution. There is a reason why it is called a student. You can just Google it and get your answer. It's because of Gossett and he has t ending with his name. So many people oppose that he cannot name this under by taking his name. So I just use the last letter and call it as T. And he said, I'm you know making this in favor of all the students who are studying the teaching period at that particular time. We have chi-square. So this is chi, again a Greek letter, and then f. And while discussing standard normal distribution, I talked about notation, and I said Z will be used, and I also said that here onwards we'll be using special symbols in order to indicate the variable. So when we talk about normal or standard normal distribution, any normal could be easily converted into standard normal. So whether it is normal or standard normal, they mean one and the same. So you have standard normal, you have student's t, you have chi-square, you have f. Now let me show simply how they are related and why do we need only these distributions. So I said, if you have normality, only then these things could be achieved, and all the hypothesis testing formulas or your estimation formulas are either from the t distribution or chi-square distribution or f distribution or z distribution. So that's why you need the assumption of z. So this is the reason, these are the reasons why the normality assumption is very much required when you're dealing with the parametric inference. Now, standard normal distribution you have. So you have x follow normal with mean mu and sigma. Then we define z as x minus mu by sigma. So you take the z and you square it. That produces what called as a chi-square distribution. And in most of the cases, these distributions which are derived from standard normal distribution has what called as degrees of freedom, and they simply mean number of variables used in producing the distribution. So how many variables you are using to come up with such distribution? So I have one set of x from which I have produced z, and I'm just using one such set, then that distribution will be chi-square with 1 degree of freedom. If you have another z, say z1 and z2, then you can talk about z1 square, which is chi-square, z2 square, which is also chi-square with 1 degree of freedom. And mathematical property tells that if you look into the sum of this chi-square, that is also chi-square, provided you are dealing with the independent variables. So we have 2z here, z1 and z2. So I have squared the z and I have added them. If z1 and z2 are independent, they become chi-square. Now it is 2. So I've used 2z, therefore degrees of freedom is 2. Now similarly, if you're using n such variables, say z1, z2, z3, etc., zk are k independent standard normal variables, only then I can produce a chi-square. So in that case, my chi-square is defined as the sum of all the square of these independent variables. And since I'm using k variables, the resultant distribution chi-square is said to have k degrees of freedom. So I can generate a chi-square only from standard normal. So if your data is not normal, then you cannot produce standard normal. You cannot produce chi-square. Okay, so this is how the chi-square is defined. Now, definition is simple. So you can come up with always the PMF. So if I say I have a normal, then that variable will follow the rule like 1 by sigma square root of 2 pi e power minus half x minus mu by sigma whole square. For binomial, you have ncx p power x q power n minus x. Similarly, you can come up with the PDF of chi-square, and that is also in a functional form. That is very much simple. So I'll have e power minus chi-square by 2, chi-square to the power of n by 2 minus 1, and we use a mathematical function which is called as gamma function, as you have factorial, you have what's called as a gamma function. A gamma and factorials are closely related when you have dealing with integers. Need not worry about this structural form, but just remember there is a chi-square distribution. It has its own PDF, it has its own mean, variance, etc. Now, so we are familiar with our x, our z, and then I have a chi-square with some k degrees of freedom. So next what I do is I use this z as well as this chi and see what happens when I take the distribution of normal over the square root of chi-square. So this is how technically the t distribution is invented. So basically, no one observes the functional forms first. So they will look into the values. Data irutte, sampling values irutte. But our sample values are such that though I have taken it from this, they are not, exhibiting the property of the parent. They are exhibiting some other property. So after investigating for a long period of time, we have come up with a property which is z by root of chi-square by k. Since I'm using here k chi-square variables and this, so I say this also has k degrees of freedom. So this is how our t distribution. So you can see that t is also derived from z. Now if you look into f is defined as ratio of 2 chi-square. So chi-square 1 divided by its degrees of freedom divided by chi-square divided by its degrees of freedom, that produces what's called as an f distribution. Now, if you look into the limits now, our x is it lies in the real line, which is minus infinity to infinity. Our z also lies from minus infinity to infinity. And by chi-square, I mean z square. So even if you have negative values, when you obtain the square, you get only positive. Therefore, your chi-square always goes from 0 to infinity. So your symmetric nature of normal is violated here. And the next case, if you have a z and your chi-square is positive, root of a positive quantity is also positive, but z is both positive and negative. Positive and negative by positive always leads to positive and negative. So your t has a range similar to normal. So this t and z are very closely associated. They almost share most of the behavioral properties of the distribution, but only changes in terms of skewness and kurtosis. And then these are all, ratio of two positive numbers that also takes the range 0 to infinity. So all these are called as sampling distributions, and they have a very close association with standard normal distribution. These are the not only, sampling distribution. We are talking about 4 such cases which are most widely used. When you look into a particular variable, you could have binomial distribution as a parental or a sampling distribution. You could have Poisson also as sampling distribution. But while studying this distribution, we observe that under special cases, they become normal. And once we have normal, again, they take the form of either t or chi-square or f. Now the question is, why do we need this t, chi-square or f? Now coming to the answer, if you're talking about mean, it could either follow z distribution. If you're talking about a large case, if you talk about a small sample, then your x bar actually follows t distribution. And further an assumption, normal population is required here. Here, the population need not be normal. Even in case of non-normal, the sample mean follows our z. And this was, observed, and that is given by a famous statement called as central limit theorem, which states that if you're selecting a large sample, if you're selecting a large sample of 10 values, observations, even from a non-normal population, you could come up with the values or a constant such that your sample mean will always follow normal distribution, and further you can come up with certain values. So let me say A and B. such that you can actually observe standard normal case also. So this happens when your n is large. So that's why many of the researchers insist in selecting larger sample values so that this easily happens and you can talk about various such distributions. Okay, so we have talked about this T. So now I know why I need this T distribution. So if you're actually talking about a small sample, provided your sample is from normal, only then it is T because your T is from standard normal. If you have a non-normal population, then definitely you cannot talk about T. In that case, you can go and talk about the non-parametric approach. Now coming to the next case, proportion. So as said, proportion is a statistic. It also has its own mean. It also has its own variance in a large scale. And when we talk about proportion of items, proportion of people, usually we talk in large sense only. So usually we talk about large size here. Even if you say that uh, my size cannot be large, then think about what proportion you're actually dealing with. And in most of the cases, whatever the characteristic you're dealing to find out the proportion, in all the cases, you can easily, increase the sample size. So whenever we talk about large proportion, the proportion also tends to follow the normal distribution, which could be converted into standard normal distribution. Now you have selected the sample, but now you are interested in the property called as variance. And if you look into the possible values of variance and its behavior, it say follows chi-square distribution. And if you want to talk about equality or the ratio of variances, two different variances that follow the distribution called as F distribution. So that's why we need these basic distributions called as chi-square, T as well as F distribution. Now, you know the concept of estimation as mathematically brought down to a simple, I could say a circle where you're dealing with either mean or proportion or variance. If you want to talk about mean, you see whether your population is normal. If it is normal, then you can select a small sample and you can deal with the estimation process because if your population is normal, a small sample is enough to observe the properties. Therefore, we talk about, various cases, various applications of T distribution. On the other hand, you're dealing with a non-normal population, but you want to know what is happening to the population mean. In that case, select n sufficiently large so that your x bar becomes normal and you can talk about estimations like interval estimation or hypothesis testing. So you're talking about percentage proportion of certain quantity, pick large size n, observe what is the proportion, use the normality assumption, and you can produce the required results. Similarly, if you want to talk about variance or set of variances, in that case, we use what called as F distribution. Now, putting this into the formula, we talk about the hypothesis testing. So we'll not talk about much about the estimation here. I'll leave the interval estimation, but usually, when we look into the estimation of mu, which is population mean, we talk about what called as confidence interval. So you're giving an interval. Your interval is such that you can give guarantee the probability of that a particular, case where your mu belongs to that. So we could come up with 95% confidence interval, 99% confidence interval, 90% confidence interval, and so on. So you are giving guaranteeing that these many times your mu will lie in that particular case. So let me just give you a simple, simply this 95, 99 are all defined as 1 minus alpha into 100% confidence interval, where you can take alpha as the marginal error which you are interested in making, say 5%, 2%, 1%, 10%, 8%, etc. So if you take alpha as 5%, so 5% is numerically 0.05, 1 minus 0.05 is 0.95, 0.95 into 100 is producing 95% confidence interval. Similarly, if you take alpha as 2, you get 98% confidence interval. Alpha 1%, you will get 99% confidence interval. You cannot produce 100% confidence interval because there will be some error. So as we observed, our decision is solely based on only one observed value of mean. We are not observing all possible values of x bar. So that marginal error will be there. As far as possible, you can reduce it, but you cannot completely come out of this. Now, what is this 95% interval, confidence interval of mean or proportion is it indicating? That's indicating that if you do 100 sample of size the same fixed quantity n, then in 95 such cases, your mean will follow, or mean I could say will line, or I could say your population mean will line in that interval, whatever you are producing. That means, so if I say my confidence interval for mu is 3.624, and if I say this is with a guarantee of 95 case, that happens, that is indicating that if you are selecting 100 samples, and if you compute 100 sample means, and if you're doing an estimation that your mu is same as your sample mean, then in 95 such cases, your true value of mu will be observed here. So the remaining 5%, there is no guarantee that it will lie here. So by chance, if you have selected that particular sample, which is not producing the desired value of mu, then we could go ahead. That's why we say take the sample sufficiently large and take the sample in a statistical method. If you're doing that, that error could be reduced. Now, another way is to increase the confidence level. But the problem in increasing the confidence level is that your interval becomes much wider. Now, the same problem, if I say now it is a 95%, so earlier I said it is 3.624. Now you see the gap has increased 3 to 4.1. If you want to produce 99.99 confidence interval, you could end up getting say 2.5 to 5. So you have come across a problem now. So if you want very accurate, your interval will be large. If on the other hand, you are somewhat, managed with 95 or 90, in that case, your interval becomes shorter and shorter. So how this estimation is done, what is the formula, that is not required in this class. So if you have interest in that, you can look into the interval estimation, can talk about estimating several set of means, the sum or the difference of the means. You can talk about proportions, difference or sum of the proportions, and so on. Now, right now, we'll look into what's called as hypothesis testing. So we have come up with this number called as alpha, which is called as level of significance, and it is also called as probability of type 1 error, and it is opposite to the confidence level. 1 minus alpha is your confidence level. So let us look into the hypothesis testing cases. So this is an important part here. Hypothesis testing, you will have a compulsory question. So things discussed till now, they are just the basic knowledge to make you understand the concepts of hypothesis testing. But when it comes to the questions like explain hypothesis testing, you will have very much, very basic things associated, and they could go ahead and ask you the particular testing procedure for mean or proportion or variance and so on. So let us look into the basic concept. So first concept associated is level of significance or confidence level. That is, what is the marginal error you would like to commit in doing this particular test, and we somewhat try to minimize this, and we fix this as a minimum quantity, like say 5% or 1%. So basically they are just a probability. So we also call this as type 1 error. We're looking at that in detail. So this is called as probability of type 1 error. What is this error? What is this type 1? We'll look into this. So first we'll understand what a hypothesis is. It is just a simple statement. So it could be any statement, and if it involves the concern regarding the population parameter, then it is called as a statistical hypothesis. So when I say statistical hypothesis, It should be a statistical statement or a mathematical statement involving a statistical parameter. Statistical statement, or you could say mathematical statement involving a statistical parameter or a statistical population. Then such statements are called as hypothesis. Say weight of student is below 10 kg. So this is a statement, but here this is not a statistical statement because your concern or your concern is just about a particular kid, and statistics does not deal with individual. So to make it a hypothesis, you can add the word called as average. Okay, and in most of the research concern, you will have you have to prove that on an average, this is happening. Most of the smokers are drinkers. So you are not concentrating on a particular smoker or a particular drinker. Out of a large case, you are telling maximum in most of the cases it is happening. You are talking about a proportion, you are talking about an average, or you are talking about a particular part. Only in that case, you can call that as a statistical hypothesis. So here, my concern is I have to prove that average height of a student, average weight of a student is below 10 kg. I'm talking about particular set of students who are, in a case where just starting their schooling, etc. So that is what our hypothesis is. Now you can simply write this using the mathematical equations or the symbols. And I said my average population average is indicated by mu. In a particular concern, my variable is weight. So in this case, I'm indicating mu as average weight. If you talk about height, then also I can use mu. There, conceptual wise, you are using mu to indicate the weight. And if you're talking about together height and weight, in that case, you can use mu1 and mu2 or mu and alpha, some other notation. So I'm telling mu is strictly below 10 kg. So this is how simply we can convert the English statements regarding the statistical hypothesis into mathematical form. Now our concern is to check this. Is this true or is this false? So this is what I have to establish. So if you are really talking about average weight, and while giving you the foundation, I said your x bar is very much close to mu, and in most of the cases, it takes the exact value as that of mu. So if you want to prove that average weight of set of students is below 10 kg, so you already know how to achieve that. So select some students, say 10, 20, 30 students. You extract the weight of all those 10 students and you come up with the value of x bar. Now you could come across various values like this. I'm not interested in all, I'm just giving examples. So let me say I have got an answer like 9.8. Okay, so now sample mean is observed to be 9.8. So I can say yes, this is true, but it need not be. If you repeat the same experiment of selecting the another set of 10 students, you could come up with an answer x bar as 10.2. Now you cannot change your decision to false just by observing the sample. So what this example is telling is that whatever the value you observe, that is only because of chance and only because of the sample. But is this giving me really a true picture of this? Is 10.2, whatever I have observed for sample, is this telling me actually my population mean is below 10, but because of this sample I have observed this? Or is it telling me actual mean is 10.2 only, therefore this statement is false? So that testing of the validity of the statement is called as hypothesis testing. So I've come up with the framework. You have to prove that by using the sample values. That is called as hypothesis testing. Now, various hypotheses could be constructed for your means, proportions, variances, and as known, particular statistic will follow a particular distribution. So you can use your Z and T distributions if you want to talk about hypothesis testing based on sample mean. So you're actually testing mu. In that case, you can use Z and T. If you're testing any population proportion, then you can use the distribution Z. If you're talking about testing variance of a population, in that case, you can talk about chi-square. If you want to talk about ratio or equality of two set of variances, you can talk about F distribution. And we also know that your Z produces Z itself. So you pick certain Zs, you add them, that again produces Z. So standard normals, yesterday we saw that they are almost same. So I had kgs converted into Z, they become minus 3 to 3. I had height in centimeters, they had standard normal. The number of defectives in standard normal, they are unitless. So whenever you observe and if you quantify again with respect to mean, you will see that they are also producing the same Z, of course with mean same, but variances will be different. So we'll observe variance. Of course, you can see that if this is 3, this is 3.5, this is 2.9. When you simply add, you'll get a value close to 12. So Z is not at all taking the number around 12 by mean, by this statement. This equation tells that your variable is normal, but your variance is not 1. So you can reduce that now, divide everything by the variance, and then you can achieve normality there. So mathematical concepts, techniques are there where you can talk about the normality as sum of normality. So you are talking about x1 bar plus x2 bar. So that could happen for the sample mean also. So if it is happening for a set of variables, it could happen for it should definitely happen for a set of statistics. So you can talk about x1 bar plus x2 bar, x2 bar, x1 bar minus x2 bar. So all these are also called as statistics because they are basically the function of sample values. So these will help you in identifying the cases where you're dealing with multiple populations. You want to see whether they are same, whether they are different, what is mu1 plus mu2, what is the maximum it can take. So all such cases could be easily observed. So if you're talking about a single sample mean, or if you're talking about two, let me bring the concept of two here. Two sample means their equality, etc. Even in that case, we use this Z, P, and cases. Now, for the sake of examination, you will have a problem on P test. So we'll come to that. You will have a problem on Chisquare test. So one from each section will be there compulsorily. So you have to please be, concentrate on the cases when I talk about P and Chisquare. We'll now extend our lecture into understanding the other aspects of this hypothesis testing. So we have just understood the term hypothesis, and when it comes to statistical hypothesis, they are categorized into null and alternative hypothesis. These are the groups made based on what you are observing, what you want to prove. So the hypothesis, which are statements such that it is talking about an existing or prevailing condition. Existing or prevailing condition, those statements make what called as a null hypothesis. So the logic is very much simple here. Till now it is happening. So even in the near future, this is what is going to happen. But on the other hand, you are talking about a case. Till now it was true, but now my data is suggesting that it is no more true. So the picturization has changed. So if you want to talk about anything new, or if you believe that changes are there, changes are coming to the scenery, in that case, such statements which come under those cases, they are called as alternative. Example, say average marks of a student, average marks of a student who tops a particular school or university or a college. Till now it is observed to be say 98% or 98 marks. So the toppers, their average till now it is observed to be 98%. But you feel that nowadays, because of online classes and uh, students not productive at home, and maybe because of other reasons, the average marks of the toppers have come down. So average mark of uh, student enrollment. Okay, could tell the set of subjects. Average marks of students who top, that is actually come down from the existing 98%. So this is a null hypothesis. This is the alternative hypothesis. So now if you feel that the students have become more studious and they are very much into their studies, then if that is the belief, then you can say that it has changed to 98%. Now, sometimes you're not sure whether it has gone up or it has come down, but definitely you have your data which is telling that it is not equal to 98. In that case, you can say the alternative is 98. So to simply make it understand, make the concept simple, we'll always put the equality to this and uh, non-equality less than or greater than to the alternative case, but that may not be so. Till now, I have observed the maximum marks scored by the students as 98. So this could be a prevailing condition. So up to 98. Now it has come down. So that could be also a case. So don't think that always your statement which has equality or equal to sign only, they are null. You could have greater than and less than sign also in the null hypothesis. But since we talk about up to cases greater than or equal to, simply to make the concepts very much clear and easily accessible, we just stick to equality there. So this is about null hypothesis and alternative hypothesis. Your statements regarding the parameter which are such that they are giving you or they are making sense with respect to the prevailing conditions, then those statements are called as null hypothesis. If your statements are such that they are, telling you a change which has happened or a data, you have come up with a data which is suggesting whatever you observed till now that is not true or it is no more true, it is going to change, then that statement, those statements, they are called as alternative hypothesis. Now, further, these hypotheses are also broken down into what's called as simple hypothesis and complex hypothesis. Simple, when you say you have dealing with parameters, and in most of the cases, parameters are known here, or you have prior data, prior experience, which is telling your variance is this, your mean is this. So in that case, we say the hypothesis concerned about those parameters, known parameters, they are called as simple. If you have set of parameters where certain cases are unknown or values are unknown, in that case it becomes complex hypothesis. Simple. So may I ask the question, when we know the parameter, why we have to test it? So we are talking about the case of multiple parameters. You could have multiple parameters, some are known, some are unknown. So if say a simple example could be for a normal distribution. So you want to say the mean of the normal distribution is equal to 100, where you know the variance. So you know this from the past experience, or you know the population because of which you are taking this. So this is called as a simple hypothesis. Let me not write H0 H1. So I have a case where I say mu is anything above 100, but sigma square is anything say below 10.5. So you don't know the actual value of sigma, but you're dealing with the testing of mu. This is the extra information which you should have, because as said, the distributions are built not only based on the mean, they are built based on the variances also. So it is important you should have knowledge regarding or a value regarding that. So here you precisely you know, here you don't know. It could be 2, it could be 3. So what exactly is it? That has to be obtained, that has to be estimated. So in that case, we say the hypothesis could be complex. So you could have a complex null hypothesis, simple alternative. You could have a simple null hypothesis, complex alternative, or both your null and alternative are simple. So we indicate this null hypothesis as by H0 and alternative hypothesis by H1. And to make the things very much clear, we usually use the equality signs to indicate the parameter value. We use not equal to, greater than, and less than. Now the tests are produced based on a fixed level of significance. That is the chance what you are taking to be wrong. Significance. This is alpha. So this is indicating what is the error margin. How sure are you? So that is our alpha. We fix this. Now we are in a situation of testing some hypothesis, and I said there is some marginal error involved. Let us see what are these errors. Now always, we can end up making very bad decisions or incorrect decisions. So these are the 4 decisions you can take. Now case 1, actually your H0 is true. Actually your H0 is true, but your sample is generating the mean, which is telling you it is far away from the population mean. Therefore, you make or you take a decision of rejecting that, and that is called as type 1 error. So what is this type 1 error? Rejecting the true null hypothesis. So whenever we see that the hypothesis is true, we have to accept it. That is, the prevailing conditions is what till now we have observed. Those conditions, will also be there for certain number of time in future. Then I have to accept that. But my sample is a faulty sample, or maybe because of other reasons, I have made a decision of rejecting the null hypothesis. Therefore, that is an error. On the other hand, you will reject the null hypothesis when your H0 is actually false. So H0 is actually false. Your data is also giving you that evidence. So you will take a correct decision there. H0 is true, you will accept. So data is supporting you. You are making the correct decision. On the other hand, your H0 is false, but you are accepting that. That is called as type 2 error. And if you look into the probabilities associated, now since these are the 4 cases, increasing value here will lead to a decrease in here. A decrease or increase here will have an adverse effect. So you cannot actually control both, but you can try to minimize them as far as possible. So that's why we fix this type 1 error like 5% of the time or 1% of the time or 10%. So what is that indicating? That is indicating that if you follow this particular hypothesis testing procedure, what I have said, and if you do that 100 times, only 5% of the times your decision is wrong, and whatever the decision you have made, that is 95% times true. And hence, in most of the medical cases, they talk about 99.9% accuracy rate or 99% accuracy rate, which is 1 minus alpha. So if you take alpha as 0.005, 0.5%, 1% or half percent, in that case, it is telling that out of 100 such cases, in most 99 cases, this is what is true. Therefore, we accept this is what is happening. So this is about the errors, type 1 error, type 2 error. This is just the definition. If you bring in the concept of probability to that, then we can actually define alpha as probability of type 1 error, which is also called as level of significance.